Hello class, this is lesson 5-6 in our textbook titled Inequalities in Two Triangles and Indirect Proofs. So there's actually two different things that we're going to be going over, and so let's just start with inequalities in two triangles. Okay. At the beginning, I have right here, it's kind of my own version of a gate, okay, where there is a fence and then there's the door for this gate in the fence, and we know that you can open a door pretty far. So right now, just where it's labeled, you can see that the distance from B to A is going to stay the same. Also, the distance from C to A is going to stay the same. The thing that's changing is the distance from B to C. And right now it's a very short distance, so this angle right here at angle A is pretty small. Well, as I open this gate even further, you can see the distance from B to C got even further, and also angle A down here at the bottom got bigger as well. And the gate can open even wider, and now it's a really big angle and a really big distance, and sometimes you can move that door for the gate pretty wide. So the distance from B all the way to C is huge now, and this angle A is a very, very big angle as well. And what this is bringing us to is called this hinge theorem, okay? Kind of like the hinge on a gate. That's where it gets its name. So let me show you our first theorem for today. It's called the hinge theorem. It's theorem 5.13, and it says if two sides of one triangle are congruent to two sides of another triangle. So in my two diagrams, or my two triangles, I have this one side with the blue marking is congruent to the other side, and same with the one with the two green markings is congruent to the other side. So I have that. And also, if the included angle of the first is larger than the included angle of the second, so included means the angle that's formed from those two sides, and the angle that's formed from those two sides. So if the first one is larger than the second one, then the third side in that first triangle is going to be longer than the third side of that second triangle. And that's what this theorem is stating. Okay, based on this hinge, as you extend this angle, the distance across it is going to get bigger than if you keep the angle smaller. So in this case, I'm just going to write that Wx in the end is going to be greater than the distance st. Okay. There is a converse to this theorem, and it is theorem 5.14. The converse to the hinge theorem. And it's very, very similar the way that it starts out. You're going to, again, have two sides of one triangle congruent to two sides of another triangle. But this time, we're given that the third side in the first triangle is bigger than the third side in our second triangle. If that's the case, then the included angle of the first is going to be larger than the included angle of the second. So that means that angle C is going to be greater than the measure of angle F. That's the conclusion that we're going to make from this converse. So let me give you an example then, and let's see if we can work it out. So what it says is if ST is congruent to PR, so ST is congruent to PR, how does angle PST compare to angle SPR? So angle PST is this one down here on the bottom. And how does that compare to SPR, which is this angle up here? Okay. So let's just think of some things that we already know. We know that ST is congruent to PR, because that was just something that we were given. We also know from the last chapter that SP is congruent to SP by the reflexive property of congruence. Okay. And since this side, PT, is 20 inches, since I know that that is greater than 14 inches, I can assume then that PT is greater than RS. And this is basically what I was given up above, that if I had two sides, let me just pull this down, if I had two sides in a triangle that were congruent to two sides in another triangle, which I've shown here, and also if the third side was bigger than the third side of the other triangle, then I can assume that the measure of angle PST is greater than the measure of angle SPR. And that's by the Converse Hinge Theorem, Theorem 5.14. So if you were asked to do something like this is just kind of what you would do. You would think back. It's not a formal proof necessarily, but it's your reasoning. Well, I know that two sides were congruent, and I could compare the third side based on what I was given in the diagram to therefore make a conclusion from one of the theorems that you were given. So this is kind of all that we're going to be doing for comparing these two different triangles. And now we're going to move on to something different. Okay, so far we've been reasoning directly to prove information to be true. That's what we've been doing all along this year, was just stating, oh, this fact is true, and this fact is true, and this fact is true. And so now we're going to move on to something different. It's called an indirect proof. And in an indirect proof, you're going to assume the conclusion to be false to eventually lead you to a contradiction. And then, because that leads to a contradiction, that must make the original conclusion to be true. Okay, so it's kind of playing devil's advocate in a way. So there's 3 steps that we're going to follow to help us write our indirect proofs. So the first step to organize our thoughts is to assume temporarily that the statement you want to make is false. Okay, so whatever it's telling us to prove, we're just going to assume temporarily that that's false, which means that the opposite is true. Okay. Our second step is we're just going to work through, we're going to reason logically until you reach a contradiction. Okay, that's what you're going to do. You're just going to say, oh, well, you know, this and this is true and this is true. Oh, but then this leads to something false. So because of that, you're going to point out that the desired conclusion must be true because the conclusion that you proved about your temporary assumption was false. So we're going to end with one example related to this. And then you're going to get a lot of practice when you go to class later. So here we go. It says to write an indirect proof to show that the sum of 2 odd numbers is even. Okay, this is what we're going to do. It's not going to be a formal proof. We're just going to kind of write out those 3 steps. What we're given is that A and B are odd numbers, and it wants us to prove that A plus B is an even number. Okay, so remember step 1, whatever we're asked to prove, we're going to assume temporarily that that's false. And that's what we're going to write down. Assume that A and B is not even, which means that A and B is odd, or A plus B is odd. Okay, so that's going to be our first step. Let me move this up a little bit. So then our second step, it said to just kind of work through what we were given to hopefully try to reach a conclusion that is false. So I'm going to do this with you. So for step 2, what I'm going to write is that if A plus B is odd, then that means A is equal to 2m plus 1, right, for some number m, and also B, if it's odd, it's going to be 2n plus 1 for some number n. So I'm just going to work this through. So that means that A plus B is going to be adding those together. So 2m plus 1 plus 2n plus 1. And when I kind of put those together, I'm going to get 2m plus n plus 2. This is even. So Even though I started with two odd numbers, I showed that when I added them together, it was even. And this right here contradicts the assumption that a plus b is odd. So do you see how I just worked through this rationally and then came to a contradiction for what I was assuming? So the assumption that a plus b is odd must be false, which means a plus b must be even. And this is how you do an indirect proof. Okay, so come with any questions that you have when you come back to class tomorrow, and I'll be happy to answer them, and we're going to do a lot of work on this together.